Hello, back at you for a second video. This will be a short one, but I wanted to kind of both take a step back and also then take a step forward. And so the step back is really kind of asking a pretty important question that hopefully many of you sort of thought in the back of your head as we kind of go through a lot of this. And so the big question is, why is it important to understand Mendelian inheritance? We make a big deal out of all the experiments that Mendel did and sort of how that allowed us to understand how traits are passed down between generations. And while it's important to understand a lot of that, I think it's sort of also important to think about why else is this important? What does this allow us to do? And so generally, this does allow us to understand how many, but not all traits are inherited. Okay, so kind of a key point here, and this will serve as a little bit of a springboard moving forward. Many, but certainly not all, and actually I would think that maybe, at least in humans, the minority of traits are passed down this way, but many, but not all traits are inherited in a Mendelian fashion, or this is kind of a fancy way of saying way. Okay, so many but not all traits are inherited in a Mendelian fashion. Okay, and so this includes traits in all sorts of different organisms, plants and animals. And so you can really start to think about applications of Mendelian genetics. And so let's think about agriculture for a second. So in many ways, there are desirable traits in either plants or animals that we use in agriculture that we want to pass down. And so many of those traits are actually passed down in a Mendelian fashion. So the better that we understand the inheritance of those traits, the better that we can actually engage in things like artificial selection for desirable traits. Okay? Likewise, you can sort of think about applications for Mendelian genetics in humans. Okay? Many, but not all, disease traits are actually inherited in a Mendelian fashion. Okay? So if we want to understand the way that particular disease traits are passed down from generation to generation, it helps to understand really the underlying principles of Mendelian inheritance of these traits. Okay, so this is just kind of a step back to give you some idea of the broader importance or broader relevance, I think, of Mendelian genetics. Okay, so when we talk about these applications, a lot of times we're discussing ways in which we can kind of predict outcomes. Okay, so we're predicting inheritance outcomes. And so you can think of these really as Mendelian genetics problems. Okay? And so what I want to do now in this short video is talk about two important tools that you need to have in your toolbox to approach these Mendelian genetic problems. So the first one is something called the product rule. And the second one is something called the sum rule. Okay? So I'm going to go through sort of what each of these are, and also a couple examples of how to use either the product rule or the sum rule in these Mendelian genetics problems. Okay, quick aside, I'm actually on the hunt for a bigger eraser. If I find one, I'll let you know. Okay, so let's talk about this first one, this first tool in your toolbox that you need to have. And that's known as the product rule. Okay, so what is the product rule? Okay, so its definition is the probability, and we're going to be talking a lot about probabilities as it comes to predicting outcomes. We're going to be predicting the probability of various outcomes. Okay, so the product rule states that the probability of two or more independent events occurring together is the product. You should think multiplication here probabilities that each event will occur by itself. Okay, so the couple key words here, these are independent events, and you should recognize this term independent from the last video, the law of independent assortment. So the assortment of different genes during gamete formation are independent events. And then also, again, this product, come back to this. So the product, which is really the multiplicative product of these two events. Okay. So a simple example of this, we'll call this example number 1. Let's think about coin flips. Okay. So let's say, what is the probability of flipping a coin and getting tails 3 times in a row? Okay. So tails 3 times in a row. Okay. So flipping a coin once, and then flipping the coin again, those are 2 independent events, okay? So the outcome of that second coin flip in no way depends on the outcome of that first coin flip. No matter how much we try and talk ourselves into the idea that we're due for sort of a tail, if you get like 5 heads in a row, you're due for a tail. No, there's still just a 50% chance that you're going to get a head or a tail, okay? So, now let's apply the product rule to this very simple example. Okay, what is the probability of getting tails 3 times in a row? So each of those 3 coin flips are 3 independent events. So we know that the probability of getting a tail equals 0.5, 50%, 1/2. All these are just different ways of saying the same thing. They're all just sort of different versions of fractions. Okay, so the probability of tail is 0.5. So probability of 3 tails in a row is 0.5 times 0.5 times 0.5, which equals 0.125 or 12.5%. Okay? So that's a very simple application of the product rule. Okay? So now let's think about the product rule in terms of something a little more relevant to genetics and stuff that we've talked about. Okay, so let's go back to our Northeast Iowa river slugs. Really just right up there in the pantheon of genetic organisms like Drosophila, C. elegans, Arabidopsis, and the Northeast Iowa river slug. Okay, so let's think about our slug dihybrid cross. Okay, so in our dihybrid cross, we crossed our 2 dihybrids, which were both hairy and irritable, but they were heterozygous. Both hairy and irritable, because each of those are the dominant phenotypes for these 2 traits. Okay. So what is the probability that a progeny slug is both smooth and irritable? Okay, so you can already see we generated our 2 events here. Okay, smooth is one event and irritable is one event. Okay, so I'm going to show you in this board a little bit of a shorthand way of going through this, and this is something that I want you to be familiar with. It's called the fork line method. Okay, it's really just a way of separating out these dihybrid or multi-hybrid crosses as you get a lot of these different traits kind of piled up together. Okay, so this fork line method, I'll show you how to do this first, sort of according to phenotype. So basically, it's a way to split things kind of into separate events. So event 1 and event 2. Okay, so event 1 is going to be whether or not our progeny slug is either hairy or smooth. Okay, so this is hairy versus smooth. And then event 2 then is going to be the second event, which is whether or not our progeny slug is irritable or chill. we can basically just list out the probabilities, and we'll end up creating this fork line of all the different probabilities throughout this. A different way to visualize this. So we'll separate this out into our two possibilities for the first event, hairy, smooth, and then off of each of those, we're going to fork into the different possibilities for the second event. Okay? So two possibilities for this first event, irritable, chill, and then two possibilities for this event down here. Same one, irritable and chill. Okay? Okay, so we know that the probability of a slug, if we just kind of look at this first trait of the coat, we know the probability from a dihybrid cross of one of those slugs being hairy is 3/4. Okay? Because that can be a product of either, that can mean that the genotype is either homozygous dominant, or it could also be heterozygous. And so those are three in our phenotypic ratio of 3:1, these are the three. And then smooth, the probability here is 1/4. Okay? Then we have the same probabilities when we look at the other trait, the demeanor of the slug. Okay? So there's a 3/4 chance that the slug is irritable and a 1/4 chance that the slug is chill. Okay? And we have those same possibilities for each of these two events. Okay? So now with the product rule, going to this fork line method, we can just identify our events and then multiply. Okay? So first event is smooth. So what's the probability of our slug being smooth? Well, we've listed that out. That's 1/4. Okay? Second event, event 2. The probability of our slug being irritable, well, that's 3/4. And we've calculated it out right here. Okay, so we can simply then do the multiplicative product between smooth and irritable, 1/4 times 3/4, and that equals 3/16. Okay? So you remember in the last video we talked about the expected phenotypic ratios of a dihybrid cross. Okay, that 9:3 to 3:1. Well, this is one of the threes. Okay? Actually, I think since this is kind of, we'll call it this one right here. So this is one of the three. So there's a 3/16 chance that one of the progeny slugs from this cross is both smooth and irritable. So that's an example of the product rule as it applies to a genetics problem. Okay? All right, so we're going to move on to the second tool in your toolbox, and that's the sum rule. What does the sum rule state? Okay, the sum rule states that the probability, again, we're talking about probabilities here, of either of two mutually exclusive events occurring. So the probability of either of two mutually events occurring is the sum, think addition, of their individual probabilities. Okay. So for the product rule, we were thinking about independent events. Independent events, for this one, we're looking at mutually exclusive events. And again, as opposed to using the multiplicative product, we're going to be using the additive sum of these two probabilities. Okay? So a simple example. Let's think about a deck of cards. Okay? So on a normal regulation deck of cards, there are 52 cards. Okay? 4 different suits, all the way from 2 all the way through the ace. So there's 13 cards per suit. Okay, so what is the probability then of, of drawing a 4 or a heart? From a deck, okay? Again, we've got two events here. 4 is event 1. The heart is event 2. Now these are mutually exclusive. You're drawing a card once, so these are two exclusive or possibilities in the case of what you're going to be doing here. Okay, so basically now we just need to calculate the probability of either this event occurring or this event occurring. So then the probability then of drawing either a 4 or a heart is going to be the sum of these probabilities. Okay, so the probability of pulling a 4 out of the deck of cards is 4 out of 52. Okay, remember I said there are 4 suits in a deck of cards, which means there are going to be 4 4s in your deck. Now the probability of pulling a heart, okay, there are 4 suits, and there are 13 hearts in the deck. So the probability of pulling a heart is 13 out of 52. So the probability of drawing a 4 or a heart is really just the additive sum of these two things. Okay, so that's 17 out of 52, which if you do the math, comes out to 0.327 or 32.7%. Again, all these things are really saying the same thing. 1750 seconds, 0.327, 32.7%. Okay, if I were to ask you a question about the probability about something and you listed it either as this, or this, for all the same thing, I would consider those all sort of equally correct answers. Okay? So that's a simple example. Let's take this product rule and let's draw it back to genetics. Okay, let's go back to our river slugs. Okay. So let's say that we crossed a slug that is heterozygous for both coat and demeanor. Okay, so in this case, this is going to be a hairy and irritable slug. Okay, so it's heterozygous for both traits, for coat and demeanor. And let's say we're going to cross this slug with one that is, let's see, heterozygous for coat. Okay, so it's still hairy, but it's heterozygous. But then also it's homozygous recessive for demeanor, so it's actually chill. Okay, so hairy, irritable, cross hairy, chill. Okay. So the question then is, what is the probability that a progeny slug is hairy irritable or smooth and chill? Okay, so here are two events. We got event 1 and event 2. So really all we need to do is calculate the probabilities of event 1, event 1 and event 2, and then add those up. Okay, so now I've added a little bit of a wrinkle here. So to calculate either the probabilities of event 1 or 2, we actually need to use the product rule. Okay, so we've got two events kind of built into event 1. We've got event A and B as part of 1, we've got event A and B as part of 2. Okay, so we're kind of collapsing these things together to make it a little bit more complicated. Okay, so I'm going to use that same fork line method that we used in the last time, but I'm going to break down the fork line by genotype. It might make it a little more complicated, but I want to show you how you can use a fork line to break things out according to genotype as well. Okay, so let's first kind of deal with the coat trait. So hairy versus smooth. So we've got 3 potential genotypes as a result, because remember, hairy is going to be looking at HH cross, or 2 hets crossed with each other. Okay, so our 3 possible genotypes out of this one are homozygous dominant, heterozygous, and homozygous recessive. Okay? Then I'm going to treat the next trait as another independent event within our sort of product rule here, and that's going to be heterozygous crossed with a homozygous recessive. Okay? So we've changed things up a little bit, so you'll notice that there are only 2 possible genotypes as a result of this potential cross. Okay, you can get slugs that are either heterozygous, so this gamete plus one of these, or progeny that are homozygous recessive, so this gamete plus one of these. Okay, and so this holds up for all 3 of these possibilities. Okay. So let's fill in some probabilities here. Okay, so out of this simple kind of monohybrid cross right here, we know that this is a 1/4 probability, this is a 1/2 probability, and this is a 1/4 probability. Again, so this kind of breaking this down to our genotypic ratio of 1 to 2 to 1. Okay. Then we go through here, and then very simply for this cross, all these are a 50% probability, or 1/2. Chances 1/2 you'll get that, either one of those genotypes, when we treat these sort of independently. Okay, so let's go to event 1 then. So event 1 is it needs to be hairy and irritable. Okay, so we know that hairy can be a result of either homozygous dominant or heterozygous. Okay, so that's 1/4 plus 1/2, or 3/4. And then irritable, well, we know that that's a 1/2 chance. It's either going to be heterozygous and irritable or homozygous recessive for chill. Okay, so 3/4 times 1/2. So this equals then 3/8. Okay, so that's our sort of, we're using the product rule to get the probability of event 1. Okay, now we need to look at the event 2. Okay, so what's the probability of our progeny slugs being smooth? Well, that's right here. It's 1/4. Okay. Now the probability of being chill, again, well, that's just 1/2 here. So we multiply that through, and we get 1/8. Okay. So to do the sum rule now, so the probability that our progeny slug is either hairy, irritable, or smooth and chill, we take this here, 3/8, we add it to 1/8, and that equals 4/8, which is the same thing as 1/2, which is the same thing as 0.5, which is the same thing as 50%. All these really say the same thing. Okay, so there's a 50% chance that out of this cross, we're going to get a progeny slug that's either hairy, irritable, or smooth and chill. Okay, so I wanted to sort of introduce you to these 2 ideas, because what I'm going to end up doing in the next day or so is actually giving you out a set of Mendelian genetics problems that I want you to work out. Okay, and so we'll turn those in for credit. I'll figure out kind of when the due date is, and I want you to work on those before we get to our next lecture quiz, because there'll be some examples of these types of genetics problems on that lecture quiz. Okay, hopefully that made sense. I'll see you next time.